Hello, this is lesson 11, part A, and this one is about different types of population growth, so not the exponential type, but limited growth. So they mentioned here that the whole idea with exponential growth is that things continue to grow unbounded, and we can think about realistically that's not something that we can expect to actually happen. So this is talking about a very crowded area here, right? So some kind of city where the growing is relatively constant at 3 to 4% per year. And then question one is saying, what happens here when the roads get crowded? We can't support that way of living and the population gets so dense. So what's going to happen to population growth? We can definitely say there it's going to slow down, right? So I'll write that down. So the growth rate is going to slow down. Notice that it's not only going to slow down, but it could actually start to decrease, right? So it could drop. This is all due to the fact that quality of life and resources are diminished, right? So we can expect the population is going to show those effects. Right, so the rest of this lesson here is really about a small set of islands, right? Smith Island in North Carolina, and it's about a deer population, right? A deer herd that was introduced there. And so it says the population started sometime in the mid-1980s, and then by 1996 there were 30 deer, right, that were present here. The interesting thing about this is it says hunting was not allowed and there were no natural predators. So what we can expect here is this number is going to sort of blow up, right? So as time goes by, if there are no predators, the deer population is going to flourish. Okay, so this is page 2 here. So it says in 2002, they found the approximate density of deer. So this is an important number here, 19.5 deer per square kilometer. And it gives you the size of Smith Island here, about 48 square kilometers. And then based on some research, they found that the densities were between 11.9 and 57.8. So you can see this number is in between. So we're going to use this number 19.5 to do some of these calculations. So for number 2, it's saying according to the study, what was the deer population on Smith Island in that year, 2002? So I'm going to use this number here, that 19.5. So we have 19.5 deer, and this is per square kilometer. Right, so we can write it that way. So 19.5 deer per square kilometer, but then they give you the size, right, in square kilometers. So if you take this and you multiply it by 48 square kilometers, then you can see just the unit analysis here, right? You're going to end up with the number of deer. So this is something you should try on the calculator, 19.5 times the 48, and you get 936, right? And the units here makes sense. It's the only units left here. We're talking about the number of deer. So this is really showing you without predators and without hunting, that number 30 goes way up, right? So notice, though, that this is after many, many years have gone by. All right, so that looks good. Number 3 is saying let's do some representation here to look at the deer population. So we're going to use the information they gave us to fill out this table. So in 1980, I think they told us the population originated in the mid-1980s. So that means here there would be no deer. In 1996, they told us there were 30. And then in 2002, we just calculated that, right? 936. So it's really kind of nice to see this, right? This is really what exponential growth looks like. It is no accident that these numbers here we're actually experiencing right now with the coronavirus, right? That we're seeing the number of cases, right? They started out at 0. They were really, really small in the beginning, like 5 or 6 or 7 cases in the US, and now that number just continues to grow. So this idea of exponential growth can be seen in many different phenomena, right? So not just populations. All right, so I want to do part B here, the graph. So it says make a quick hand sketch of the data. So I'll do that really fast. So I'm going to just maybe label the years here. 80, 96, and maybe 02, right? They look like that. And I'll call this 1000 here, right in that spot. So if you're going to graph the data and look at it, you're going to see this sort of exponential explosion, right, when you look at the data. So here we have no deer at all, right? So I'll just label these. We have the year here, and here we have the population of deer, right, on Smith Island. So in 96, we're at 30, but if you think of 30 relative to 1,000, you could barely even see that, right? And then in 02, we're very close to that 1,000. So if you were to sort of graph this, you sort of get this phenomenon, right? It's going to look like that. They do ask you here, should the points be connected? I would definitely give that a yes, right? So the population here is not going to discretely jump from these values. For example, at one point, you expect to see, say, 75 deer or 634 deer, right? So connecting these points is sort of telling you what's happening in those intermediate years. All right, and then part C, describe the rate of change of the deer population. All of that can be seen in the graph, right? So for this one, the growth rate is very, very slow at first, right? It looks nearly flat. But then it increases rapidly. So we saw some of this in the earlier lessons. And again, I'll just repeat the fact that we actually saw this in the number of cases of coronavirus, right? It was fairly flat in the beginning, and then the curve almost looks vertical, right, with the number of cases. All right, on to page 3. Here they introduce some new mathematical terms, right? Some things maybe that you have not seen before. All right, so they give you a scenario at the top. It's saying this area became more urban, right? There were more developments. And then the people that lived there started to worry that the deer population would destroy the maritime forest and then also just interfere with their way of living. And there was also an increased number of accidents, right? Automobile accidents. So question 4 saying, describe what you think would happen to the deer population between these years, right? If we didn't do anything, right? So with no intervention. So I would say here, population continues to grow, right? The deer population. Right? So the population will continue to grow, but I also feel like at the same time, it might start to slow down. And that's because all of the things that are happening on the island, there are restrictions or restraints on space, and there are also accidents, right? So I might add that. So this is important, right? Because we're saying it continues to grow, but at the same time, we're saying it grows at a slow rate. So those are somewhat conflicting ideas, right? So we're saying the population still is going up, but it's not going up as fast. All right, so number 5 is kind of the heart of this lesson. It really gets to the idea that we can have other things that are different than exponential growth. So the main thing they define in number 5 is what is called the carrying capacity. And so this here is the maximum sustainable number of deer, right, that we can expect on the island without having problems like disease or death or the fighting of resources. So researchers analyze these types of things and they come up with approximations, right? So this is the carrying capacity. So this is saying 33 deer per square kilometer. You'll remember in that earlier problem that this number was around 20, right? 19 and a half. So what that's saying is in the beginning, when they were approximating about 19 and a half deer per square kilometer, that was way below what could have been supported, right? And that's why the population continued to grow. So once you get above this number, then what you're going to start to see is some problems, right? Mass death, right? Lots of problems in sustaining that population. All right, so let's look at the questions that they have here. So let's say the deer are projected to reach that limit by 2020. And then they're saying actually go through and calculate the population of deer. So this is like the earlier problem that we did. So if you did 33 deer per square kilometer and you multiplied by the size of the island, right? This was 48. So again, you'll see a cancellation of units here, right? 33 times the 48. Check that on a calculator. You get 1,584 deer, right? So this is the maximum number that we can sort of expect. And again, all of these numbers we kind of take with a grain of salt. It might be closer to 1,600, right? So it's just an approximation. Part B, what do you think is going to happen to the rate of increase during the years leading up to the point where they reach this number? So my feeling here is the growth is going to slow. So as you get closer and closer to this limiting number, right, the growth rate is going to slow down. Even though the number of deer continues to increase, it happens at a slower rate, right? And this is again due to all those things like overcrowding, lack of food, etc. All right, part C is saying sketch the curve that you think will represent the deer population. And now it says from 1980 through 2020. So I think they were asking us here, which I forgot to do, to add our answer there. So I'm going to go back and do that here. So this is the earlier example. So I'll put this in here. This is 2020. And you can see that. So what they're asking us in this question is to plot this data, right? Let's see what this is going to look like. All right, so my feeling on this one, let's see. So again, we're going to have time here. This is going to be in years, and we're going to have the population here. So the new part of the graph that we didn't have before is this carrying capacity. So the maximum population is around this number, right? 1,600 or so. So I'm going to draw a horizontal line there to show that. And then, again, we can show the years. We had 1980, 96, 02, and then something slightly further apart is the 20. So it looks a little bit like that. So it tells us in the problem that the deer are projected to reach the carrying capacity by 2020. So what I'm going to do is right at this location here, right at the 2020, to put a dot right here so it gets very, very close to that. And what we had earlier is a 0 in this spot. We could barely see any difference here. And then in 02, we had that big jump around 900. So it's like that. So the difference in this graph is in our earlier graph, we had something that sort of looked like this, right? This looked like exponential growth. Now what we're going to see here is that the growth rate is going to slow down, right? So the graph sort of looks like this, and then is going to approach that carrying capacity. So in many things that we see in daily life, we theoretically think about exponential growth. So I'm going to kind of cover this graph. We think of this, like the population continues to grow, but what's really happening is at some point it's going to slow down, right? And then it's going to level off to whatever can be sustained. So this is the heart, really, of 11A, right? This is what this is all about. This is called limited growth. So part D is saying just to do a comparison, pretty much did that, right? So if you look at this graph and you look at this one, you can see the differences in the sharp growth here, and then it starts to slow down here. All right, there's just one more part to this. This is kind of a controversial idea, right? The culling of a population. So what it's saying here is if the population gets too large, there are going to be internal problems there. So this is the removal of animals, right? It could be by a variety of different ways. And it's surprising. It's a little bit counterintuitive, but this is done to actually help the herd, right? Because if you have a limited amount of space, there are lots of problems that can occur with that population. Okay, so this is the last question, number 6. It says, what is culling really going to look like here? So if you take these actions, right, to cull the population, sketch a new curve for the deer population from 1980 through 2020. So, you know what? I probably could take my earlier example, but I think I'll just add it on here. So they do say to do it through 2020, but I'll kind of extend this over time. Maybe I'll do this in color. So if you were to look forward here, once you reach the carrying capacity here, if you start to cull the deer, then what's going to happen is the population will probably drop here, but then you don't introduce any of those measures, and what's going to happen is the population will rise, right? It will come back, reach the carrying capacity, and then you'd have to cull again, right? So that's the basic idea. That's what the population would look like. You'd see some kind of fluctuation here in the graph. All right, that's 11A.